Hello and welcome to another video on orbital mechanics. We're doing the problems in the book Orbital Mechanics for Engineering Students. We are up to problem 1.6. Problems are finally getting into something related to orbital mechanics. So 1.6 wants us to do a very simple formula. It wants us to work out the gravitational force between two people, one of 80 kilograms and another 50 kilograms, 0.5 meters apart. So this is quite straightforward. We just use the equation for the force of gravity, which is F of G equals gravitational constant mass 1, mass 2 divided by the distance between them squared. The gravitational constant uses units involving kilograms, so we'll leave them in kilograms. So it's G times 50 times 80 over 0.5 squared. And if we just, and the gravitational constant G is equal to it's 6.6743 by 10 to the minus 11. So let's just put all that into my calculator, and we get 1.0679 micronewtons. The book says the answer is 36 micronewtons, but it's not. Like, I've checked other sources. This is the same answer that other people on the internet are getting. So that's that. Then on to 1.7 is asking if a person's weight is W on the surface of the Earth, calculate the Earth's gravitational pull on that person at a distance equal to the moon's orbit. So this is also not terribly difficult. The weight equation is W equals the mass of the object times gravitational constant times the mass of the body divided by the radius squared. And in this case, that is going to be Earth initially. So our weight on Earth is the mass times the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. And the GME is actually a value that is typically used, which is 3.986 by 10 to the 14. And the radius of the Earth is 6,371 kilometers. So if we plug in those values, we actually get 9.81 roughly, unsurprisingly. So m equals 1 over 9.81, which equals 0.1018 times our Earth weight constant. Well, we don't really need to do that, that's for the next question almost. But the weight of the moon is equal to the gravitational constant. Weight at the moon is the gravitational constant. The mass times gravity times the mass of the Earth divided by the distance to the moon. And then if we move the radius to the left hand side, we will get constant on the right So we can equate this with this. So r radius to the moon squared weight, if we were that far to the moon, equals the radius of the Earth squared and the weight at Earth. So the question looks for in terms of the weight of Earth. So the weight of if we were at the moon, would be RE squared divided by RM squared times the weight at Earth squared. And if we work out this by plugging in radius of the Earth, which is 36371, and the radius of the moon is equal to distance to the moon, it's 400 kilometers average, we will get a value of 275 by 10 to minus 6 W, well, Earth weights. That's 1.7 done. Go on to 1.8 on a new page. 8. So 1.8 is saying if a person's weight is W on the surface of the Earth, calculate what it would be in terms of W at the surface of the Moon, Mars, and Jupiter. So just going back to what we had before, we ended up with the weight of our mass equal 0.1018 times our Earth constant. And then if we take that for the weight on the moon, that will be the gravitational constant times the mass of the moon times our mass, which is 0.1018 WE, divided by the radius of the moon squared. And if you work all that out, you get 0.1654 compared to the weight of the Earth. And if you look that up, it's like 1/6 of the gravity of the Earth, which is what the gravity on the moon is. Let's do Jupiter first. Weight of Jupiter equals, again, we do the same thing. I have all the radiuses and constants written down here. So it's G, the mass of Jupiter, times 0.1018 Earth, divided by the radius of Jupiter squared. And if you look those values up and plug them in, you'll get 2.639 W Earth. So that's 2.6 times the gravity on Jupiter. And then for Mars, it's the gravitational constant, the mass of Mars, times 0.1018 WE, divided by the radius of Mars. Which, when you plug in all those values, you get 0.3794 WE. And as we know, Mars is roughly 38% the gravity of Earth. So that's that. Quite straightforward, just using the equations provided in the book. Just be careful with the units. Everything should be in kilograms and meters. Thank you. Bye.